So this is Hamad, the founder of an e-commerce startup.
अच्छा बॉयज़, मुझे मसला आ रहा है अपनी वेबसाइट में। हो ये रहा है कि एक स्पेशल इवेंट मैंने लॉन्च किया था, सेल लॉन्च की थी, तो उसकी वजह से क्लाइंट्स की यूजेज बहुत ज़्यादा हाई हो गई है, और वो भी स्पेसिफ़िक आइटम्स के बारे में। तो उन स्पेसिफ़िक आइटम्स पे जो क्यूरीज़ हो रही हैं वो काफ़ी स्लो हो गई हैं, वेबसाइट ओवरऑल काफ़ी स्लो हो गई है, एक दो क्रैशेस भी हो चुके हैं। और मुझे जो जहाँ तक लगता है वो ये है कि हर क्यूरी पे मुझे डेटाबेस से करनी पड़ रही है हिट, इसकी वजह से इशू आ रहा है। अगर इसका कोई हल है तो।
यार नॉर्मली आपको इतनी क्वेरीज प्रोसेस करने के लिए आपको लाइक हार्डवेयर ज़्यादा चाहिए होगा, बट वो बहुत एक्सपेंसिव काम है। तो आप इसको लाइक अगर सॉफ्टवेयर से हल कर सकते हो कि आप एक इन मेमोरी कैशे डेटाबेस बनाओ जिसमें आप चीज़ें स्टोर कर सकते हो ताकि आपको इतनी क्वेरीज हिट ना करनी पड़े।
तो ये डेटाबेस मेरी अपनी अभी वाली डेटाबेस से फ़र्क कैसे होगी?
हम थर्ड सर्वर आपको असाइन करेंगे जो कि हमारा कैशे सर्वर होगा। उसमें होगा ये कि आपकी जो अभी डेटाबेस का सर्वर है एंड देन आपका वेब सर्वर है, हम एक थर्ड सर्वर दे रहे हैं, कैशे सर्वर। आपके डेटाबेस को क्यूरी हिट करने से पहले वो कैशे में चेक करेगा अगर वो उसके रिजल्ट्स पड़े हैं आपकी क्यूरी के। इससे होगा ये कि अगर 100 यूज़र्स सेम क्यूरी प्रोसेस कर रहे हैं तो यू जस्ट हैव टू हिट द डेटाबेस ओनली वंस, एंड 99 टाइम्स जो आपकी क्यूरीज होंगी वो कैशे से ही रिजॉल्व हो जाएंगी।
ठीक हो गया।
Yes.
तो इससे मैं काफ़ी इंप्रूवमेंट देखूंगा अपनी वेबसाइट में।
ये सिग्निफिकेंट इंप्रूवमेंट।
तो इसको अब इम्प्लीमेंट और इसका जो ओवरव्यू है अगर वो मिल
Yes. So this is the current architecture of Hamad's website. The application server is directly calling the database server, and each time we are hitting the database instead of storing the results, what we will provide is this, the cache server here. So now instead of calling each time the database server for the redundant queries, we will be storing the results in the cache and then retrieving the results. There are basically three modules of our system: a TCP server, a parser, and an in-memory cache store. The core DSA logic lies inside the in-memory cache store. The TCP server will be receiving the command from the client, which in this case is the application server. Then the parser will be passing that command and will be instructing the in-memory cache store, whether it is storing the results or retrieving the value corresponding to the key. This yellow slot is the base hash map of our cache store. Each entry in this hash map is a bucket, which is a vector of hash entries. This is for the collision resolution and the chaining process. And the hash entry itself is it contains a key, string, and a value, which is a Redis object. The Redis object is defined as a class containing a type. The supported types are int, string, list, hashmap, set, and a bool. And it also contains a pointer to the stored data structure in the memory. Let's have a look at the project structure. This is the parent directory. It contains two main directories, include and the src. All the header files means .hpp files are in this directory. This directory further has a parser, a server, and a storage directory. And the storage directory further has a murmur hash directory, and this contains murmur hash 3.hpp. The same directory structure is followed in the src folder, but it uses .cpp files, the function definitions of .hpp files. And then we have a client which is used to test the connection with the TCP server, and then testing the commands and running the test cases. So now we are in the VS Code window and we will have a look at the code. The include directory, then we have the server directory, and we have server.hpp, the header file of the TCP server. It contains the class TCP server. and the constructor and the destructor. Then we have the main handle client function. If we dive deeper into it, we will open the source folder and then the server folder, and we have server.cpp. This contains all the function definitions which I showed you in the .hpp file. The handle client function is here, and in this function we will be calling the parser to process the received data, and then whatever the response we have from the parser, we will be sending it to the client. Now let's look at the parser.hpp, the process command function, and the tokenized function. The tokenized function will be breaking the received command in multiple tokens based on the space between them. And this is the parser.cpp. We have a command table in the parser.cpp. This is actually a hash map. Each command is mapped to a function and the minimum number of argument it takes and the maximum number of argument it can take, so that we can validate the uh, user input. Using this base table, we will be redirecting the commands of the user to the respective store, like the string store, list store, hash store, and the set store.
For sets, the workflow is pretty much the same. Let's say client is calling sadd users user 890. Parser will tokenize it into three tokens. The first token is the command we're calling on the set as set add. The second command is the key, which is users. Users is going to refer to a actual set name inside the base hash map, and the third command is just the value, or you can say the field we're inserting inside a set. And the set won't have key value pairs, it will just have values, unique values, unlike a hash map. So after that, the base hash map will take the key users. It's going to check whether users exists or not, and then it's going to return a pointer to that user structure, which will be of the type set, which we have defined inside Redis object. So once we have the pointer, we're going to locate that set structure and we're going to insert user 890 inside of that structure, and this is what it will look like. It will have other unique data tags as unique user tags as well, and we will insert user in 890 inside of it. Okay, so just a quick rundown of the code as well. So for Redis sets, here is the most important helper function we use, which is get or create set. So whenever we call a command on sets like set sadd key value, what get or create set does is it goes to our base hash map and it checks whether the key, which is the name of the set, whether it exists or it doesn't exist. If it does not exist, it's going to create a new unordered set inside the hash map, base hash map, and it's going to then return it to us. But if let's say the key we provided it does exist in the hash map, it's going to check whether it's a set or if it's not a set. If it's not a set, it's going to return null to us, because then we know that we cannot use this key as the name of a set since it already exists. And if it is a set, then we can just add our value to that set. So this is a helper function used by almost all of these functions below. These are the standard Redis methods. For example, sadd, which just adds a value to a set. It calls get or create set to check whether the base hash map contains the key we provided, which is the name of the set, and if it does, then it's going to just add the value to it. If it doesn't, then it's going to create a hash map and insert the value to it. And it only inserts a value inside a set if it doesn't exist already, because sets cannot have duplicate values. Now we also have set remove, set members, which returns all the members, set cardinality, which returns the number of elements in a set. Spop works like a standard Redis pop, which pops a random value from the set. And S is member checks if a value given is a member of the set or not. And S union, S intersection, and S difference are standard set operations which have some complex time complexities. But other than that, all of these sadd, sremove are all O1 except S members, which is ON, because we have to traverse each member. So my part in the project was implementing Redis hash maps and Redis sets and data logging. So this is the workflow of how a Redis hash map is going to work. Let's say a client calls a command for a hash map called hash set. user 890 name Hamad. The parser will take it and it will tokenize it into four different tokens. The first token is the command we're calling on the hash map. The second token is the key which is going to be used by the base hash map, and the third and fourth are the field and value for the value we're inserting in the hash map. So the base hash map is going to take the key which is user 890 and it's going to check whether this key exists or not. If the key exists, it's just going to return a pointer to us to that structure which is going to be a hash of the type hash, which is the type we use for hash maps inside Redis object. So if it does not exist, then inside the code you will see that if this key doesn't exist, then it's going to create a new hash map, and it's going to with the name user 890, and it's going to return a pointer to that. After that, once we have the pointer to the hash map, we're going to check whether the field we provided name exists or not. If the field exists, then it's going to just insert the value Hamad inside that field, and if it doesn't, then it will have to create a new field with the name Hamad. And this is how a key value pairs inside our hash map will look. We can also have other information about user 890 like name, age, section, and for example batch, address, and phone number, other stuff like that. Okay, so for Redis hash maps, I'll first show you the HPP header file so you can have a clean look of all the methods we've implemented inside the hash map. So we have hset, hget, hdelete, getAll, hexist, hlen. Len is going to give us the number of fields, exists give us if the field exists or not. GetAll gives us all the fields and values, and it's going to format it in a more readable structure. Delete is going to delete a field. Hget is going to return a field if it finds that field, and hset is just going to set a field and a value inside of our hash map. So for the code now, at the top we can see we have this timestamp utility function which helps us keeps data logs and TTLs, and then we have the hset. I'll go over the working of hset. So we provided the base hash map, and we provided with the key which is the name of the hash map. It's going to check if a structure with this name exists inside the base hash map. If it doesn't, then it's going to create a new hash map. Otherwise, it's going to check if it's a hash map or not. And this is the field and the value we pass which we want to set inside of our hash map. It's also going to check if that field exists or not, and whether that field is new or not. If that field does not exist, it's going to create a new field, and is new is going to be true, and otherwise it's going to insert the value inside that old field, and then it's going to just return a number 1 or 0 depending on whether the field was old or new. Then we have the implementations of other functions, hget, which is all similar. It's pretty much similar to hset. So hget and hdelete, deleting fields, and hgetAll is just formatting and printing all the fields and values. Exists for checking field existing or not, and length for the number of fields. So yeah, that's all for hashmap.
Now we will discuss how we are storing strings in our project. Since we've already made our Redis object and hash entry, we can simply utilize these structures to store our string. The hash entry will contain the key which the user provides us, and the Redis object will contain the data type as string and the pointer which will point to the dynamically allocated memory for the string in our RAM. To access the string, we can simply hash the string and look in the vector buckets at that point in the Redis hash map until we find the key and access the value through the pointer which is stored in the Redis object. Now looking at stringstore.hpp, we will find all the function definitions what we have defined for string, like set, get, delete, and increment, decrement. These are all function definitions for strings, and their implementations can be found in stringstore.cpp, as you can see here. And the project also has to deal with storing lists. For lists, we have a few requirements, which is to allow insertion into the list from both ends, deletion from both ends, and changing or inserting values within the list. Now for this we have two possible implementations, like array-based and linked list based. We opted for linked list based implementation as an array-based implementation has a few drawbacks. The first of which is that we would have to initialize a very long array to accommodate a lot of insertion, and if the array were to fill up, we would have to resize the array and we have to copy all these values into the new array, which would take a lot of computation. And so at all times the array would be a lot longer than the values that are actually stored in it. In linked list, that is not the case. You just store the amount of values that need to be stored.
And the second thing is that whenever you have to insert a value within the array, you would have to move or shift the values ahead to accommodate that new element. In the case of linked list, you can simply just move the pointers and accommodate for that new element. Now, as shown here in linked list.hpp, we created our own linked list node and our own linked list implementation, and the implementation is actually in linked list.cpp. Push from the front, push from the back, and all other functions. We also implemented sorting in linked list. We used merge sort as it's the fastest sort for these cases, and it is O and log n time complexity. And the list store.hpp shows the function definitions for our list store, and the list store.cpp will have the implementation for all of these functions.